Hello, everyone. This is the lecture for section 4.1, related rates. So in chapter 3, what we did really was just learned how to take a derivative. We built up our library of derivatives and skills for derivatives for all the families of functions. So that's polynomial, trigonometric, exponential, the logarithmic stuff, the inverse log stuff. We learned the product rule, the chain rule, the quotient rule. We did implicit differentiation for those things that couldn't be written out explicitly. And then at the very end, we did logarithmic differentiation, right? That was just so we can learn how to take a derivative. Notice that I didn't put too many applications in there too much. It was just solving problems with the derivative, right? That was just to learn how to take a derivative. Chapter 4 deals with specifically some applications of the derivative. So it's this chapter where we're going to be sticking it into more physical and social science scenarios. Basically, we're going to stick it into other subjects and see what it does. Okay. So the very first section that we're going to do is section 4.1, and that deals with related rates. Okay. Nothing from chapter 3 changes here. The derivative is still the instantaneous rate of change. Okay, or the slope of the tangent line. But now we're going to be sticking it into, like I said, physical and social science scenarios. Okay, so the best way that I think I can go ahead and sort of explain this to you guys is let's go ahead and just jump into an example here. Okay, so let's go ahead and take a look at this example right here. Let's say you had a spherical balloon, okay, that needs to get blown up. Okay, and as it gets blown up, the radius of the balloon increases by 1 inch every 2 seconds. Okay. One of the equations that we're going to need back from like middle school, elementary school, kindergarten is this right here, the volume of a sphere. So picture a big fat ball in front of you, right? The volume of that ball is given by that equation right there. 4/3 pi, we all know what pi is, 3.14159 and change. R cubed, R being the radius. Okay. So for this portion of the example, I'm going to do it sort of like the hard way. Okay. And I'm going to go ahead and calculate these things out. Okay. So for this table, what we have here is the very first column, or sorry, the very first row has the time: 0 seconds, 2 seconds, 4 seconds, 6 seconds, 8 seconds, so on and so forth. The second row is the radius at that time. And then the third row is the volume that's going to be computed using this equation that's in yellow for the volume of a sphere. Okay, so let's go ahead and get started. At time 0, the radius is 0, right? At time 2, the radius is 1 inch. So where did I get that from? The radius was given by this right here. It increases 1 inch every 2 seconds. So at 2 seconds, it should be an inch. Okay. At 4 seconds, this should be 2 inches, right? So that's 2 seconds, right? It grows 1 inch every 2 seconds. Okay. Should make sense from here on out, right? This should be 3 inches, 4 inches, 5 inches, 6 inches, 7 inches, 8 inches. Okay. Now, next up is the volume. Okay. In order to do the volume, what I'm going to do is I'm actually going to use Desmos to sort of help me out in my computation. So I've already set up the calculator for us. Okay. And it's just going to go ahead and calculate this volume for us. And we're just going to go ahead and put the values in. Okay. So the first one, obviously, if I put in 0, whoa, I said 0. There we go. Then the volume is going to be 0. That one's a no-brainer. So we're good there. Okay. Let's say we put in 1. 4.1887. 4.1887, and this is inches cubed. Okay, so if I plugged in 1 into my equation for my volume, this is the value I'd get. Okay, let's keep going. Let's do 2. 33.51 inches cubed. Okay, let's do 113.0, let's call it 113.1, yeah? 113.1 inches cubed. Okay. So if we see what's going on here, if we keep doing this over and over and over again, we're going to get the following value. So the next one should be 267.95. For 5, it should be 523.6 inches cubed. For 6, it should be 904.8 inches cubed. Let's go to 7. That's going to be 1436. And then the last one, 2144. Okay. Let me go ahead and put this right smack dab in the middle again. All right, so there we go. We can see here in the table that we have, right, that the as the radius increases, the volume is increasing, right? That should be a sort of like a no-brainer, right? And that makes sense because we're sort of pumping this balloon up, right? Okay. So for part B now, let me stop scrolling there. Come on, there we go. For part B, what I'm going to do is I'm going to look at the rate of change in the volume. So I'm going to look at how quickly that is increasing. Okay, and we're going to do this by approximations. And how I'm going to do these approximations is sort of based off of this sort of example right here. Okay, I'm going to try to write really small so that the entire math can sort of fit in there. Okay, so if I want to find f prime of 6, so if I want to find the rate of change at exactly 6, I'm going to be using this value and this value. I'm going to find the slope between these two values. Okay. Hopefully that makes sense. Okay. So what I'm going to do first, right? So if I wanted to find f prime of 0, I'd need this one and the one before it. So this one's going to be the one that's basically not there. This one's not going to exist. We don't have a value before it, so we're just going to go ahead and cross it out. But we do have f prime of 2. Okay, so f prime of 2 is going to be, using our example here, right? F of 2 minus f of 0 all over 2 minus 0. Okay, now we're going to go up here and we're going to look. This is going to be 4.1887 minus 0 all over 2 minus 0. And this gives us 2.095. Okay, and this is the units for this. We're looking at a change in volumes, right? So this is in inches cubed per second. Okay, let's do f prime of 4. Okay, so f prime of 4 is going to be equal to, I need f of 4 minus f of 2 all over 4 minus 2. So then f prime of 4 is going to be 33.51 minus f of 2. So that's the 4.188 all over 2. That is going to be equal to 14.6605. Okay, let's go ahead and do f prime of 6. We have, this is what we were using as our example. So f prime of 6 is f of 6 minus f of 4 all over 6 minus 4, right? According to our table above, it should be 113.1 minus 33.51 all over 2. And this should be equal to 39.77. 39.77. I'm going to go ahead and write one more time. Inches cubed per second. Okay. This is the math that's happening in here to sort of expedite the process. I've got the rest of the values written out, so I'm just going to go ahead and copy them over here. So this one, if you do the math right, 77.46, 127.8 to 5, 190 0.59. The next one at 14 is 265.625. These are all approximate, okay? And then the very last one, 354.315. Okay? And just keep in mind, right, that all of these, right, this is a change in volume. So these are supposed to be inches cubed per second. All of these are inches cubed per second, okay? So now what I want to do is I want you guys to take a look at this. Okay? That, let me go ahead and get rid of the highlighting here. That as the time was increasing, right, the radius was increasing, right, and those radii gave us specific volumes, correct? Okay. And in looking at the volumes, we found, you highlight these values in green here, we found how quickly our volume was increasing. Okay. So now let me go ahead and highlight the two important rows that we need to sort of concentrate on here. That as our radius changed, right, our volume changed as well. Okay. That if we were given a rate for our radius, right, we could, in theory, find a rate of change for our volume. Okay, this is the point behind related rates. That the rate of increase for one variable is entirely tied to the rate of increase or decrease of another variable. Okay, in this case, in the example I just gave you guys, we have the rate of change in a radius is entirely tied to the rate of change in the volume of the balloon. You guys see that? Related rates. That's why we call it related rates. The rates are related. Okay, so notice that we have that exactly, that the volume of the ball, the rate of change in the volume of the ball, depends on the rate of change of the radius. Okay, to solve this exactly, we're going to need the derivative. And specifically, we're going to need implicit differentiation. I know you guys hated it when you guys were doing it, but we need it. Okay, it's one of the, like I said, it's one of the most useless. It's one of the most useful things outside of math, within physics, within chemistry. Okay, there is a problem-solving process for solving these related rate problems. Okay, and I'm pulling this right out from the book. If you guys are following along with the book. Okay, so step one, right, is identify all the quantities. Identify all the quantities. Okay, I'm going to go back to our example. I'm going to sort of point out what we have and what we don't have, so we can see what we should be calling what. Okay, step two tends to be the hardest. Okay, step two deals with writing an equation that involves all the variables that you need to mess with. Okay, this is the part where we're going to need you might need to go back into your history books. You might need to go back into kindergarten, back way back. Think about way back and find the equation that you need. Okay. Sometimes it's just the volume of a sphere. Sometimes it's the area of a triangle. Sometimes it's the volume of a cube. If you don't remember them, ain't no shame. Go look it up. Google is great for this. Okay. So step 2 is the hardest. Step 3, once you have that equation from step 2, we're going to use the chain rule and we're going to use implicit differentiation to take the derivative of both sides with respect to time. Okay. And then the last bit is once you have the derivative done, okay, and you have everything in terms of variables and rates of change, you get to plug in all your values, okay, and it should fall in your lap. So step 4 is the easier part of it all, okay? So now, let me go ahead and start identifying, let me go back and sort of point out how to identify stuff, okay? Thankfully, we've already got all the variables set up, okay? So we know that time, right? Let me go ahead and do it in a nice blue here. This is, whoa, too thick. Time is our variable t, right? Okay. The radius is our r. So remember how we were needing to plug it into this equation up here, this one, in order for us to start, in order to get any of these values, right? Okay. The last one that we have is v. So notice how these, they're sort of self-explanatory, right? Okay. There are two variables here, or two expressions here that I haven't defined yet, okay? And these are the two that are sort of self-explanatory once I explain it at least once. You can go ahead and watch this as many times as you need to. Notice that from the statement of the problem, the radius is changing. So therefore, what we have here is a dr dt. Let me make that a little less thick. So we have here is a dr over dt. We have a rate of change in the radius with respect to time. Okay, this expression was given from the description of the problem. We know that the rdt is 1 inch every 2 seconds, or equivalently, half an inch every 1 second. Okay, so just keep that in the back of your head for now. Let me go ahead and define the next one down, which is this one down here. The change in volume is, whoa, not the right pen, is dv dt. So just how the top one was the rate of change in the radius with respect to time, this is the rate of change in the volume with respect to time. Okay. Okay. So now that we have those two expressions sort of defined, let's go ahead and jump into our example. So it turns out this example is exactly the thing that we were doing up above. Okay. But this time around, we're actually going to be using calculus for it. Okay. So let's go ahead and jump into this. Number 1, let's go ahead and do the 4 steps from above. So step 1 is to identify all the given quantities, okay, to be determined, and make a sketch and label stuff if possible. Okay, so we're going to start off with this. So we want to find the rate of change in the volume at t equals 6 seconds, okay? So that means the question's asking, this is what it's asking right here, right? Find the rate of change in the volume. So essentially, we are looking for dV over dt. This I'm going to go ahead and set up as I don't know. This is going to be my question mark. This is what we're trying to find, okay? We have one more value here. We have the r over dt, so the rate of change in the radius, right? That was the 1 inch every 2 seconds, or equivalently 0.5, and I'm going to go ahead and write the units here, inches per second. Okay. And the last thing is, we're going to need this. You guys will see why we're going to need this. We're going to need the radius, right, at t equals 6 seconds. And the radius at t equals 6 seconds is 3 inches. All right. Hopefully, I haven't lost people yet. Okay. Thankfully, this is in a video. You guys can watch it as many times as you want. So, step 2 is the hard part, right? Thankfully, I already figured it out. That was the equation that we've been messing with. It's this. Notice that that equation relates all the different variables that we need. Okay. So I'm going to go ahead and do this. I'm going to do by geometry, right? By geometry. The volume is 4/3 pi r cubed. This is the equation that will that relates all the variables that we need. Okay. Let's go ahead and scroll down some more. Let's go to step 3 now. So step 3 is using the chain rule. We need to implicitly differentiate both sides of the equation with respect to time. Okay. Well, this is the part that, at least calculus-wise, is the most difficult. Okay. So I need to take the derivative of this thing with respect to time. So that means that it's going to be the v over dt, okay, is equal to 4/3 pi. 4/3 and pi are good old numbers. So they get to go ahead and just come along for the ride. Okay, now we're at r. Okay. In order to take the derivative there, it's going to be, this is where the implicit differentiation happens. 3r squared, the derivative of something that's cubed, right? Times, here's the chain rule and the implicit differentiation portion, the r dt. Right here, we're essentially done with the calculus bit. Okay, let's go ahead and check with 4. So 4 is saying substitute all the resulting values into your equation, and you get the value that you need. So let's go ahead and review a little bit here. We need the VDT, right? Which means we need all the rest of this stuff to go into our equation to find dVdt. Okay, so dV over dt is 4/3 pi 3. We needed the radius at 6 seconds, which was the 3 inches. So this is going to be 3 squared times dr dt, which is 0.5. I'm going to go ahead and switch that to 1/2 because it's math. I can do that. So dv over dt, I'm going to go ahead and simplify this a little bit, is going to be, so 3 squared is 9 times another 3 is 27. 27 times 4 is, heck, I don't know. Something big. So I'm going to go ahead and write this all out. 4/3 pi times 27 over 2. You can at least write that much, right? And if you plug this all into a calculator, you should get 56.54 inches cubed per second. So to summarize, of the balloon at 56.54 inches cubed per second at t equals 6 seconds. Okay, so that is what we ended up finding. This is our answer here. Okay, and I'm just summarizing it here in just plain old English. So we wanted to find how quickly the volume of our balloon is increasing. Okay, and this is the answer right here, 56.54 inches cubed per second. Okay, so let's go ahead and just for kicks and giggles, let's go back up here to our table. At 6 seconds, right? So there's only like a couple of readings around 6 seconds that we can use, right? The change from 2 to 4 was 14. The change from 4 to 6 was about 39, right? And the change from 6 to 8 was 77. You guys see that? So our answer of 56.54 is not too far off. Just keep in mind, right, that what we did here in the table was an approximation, right? We were using slopes from the closest, nicest second, right? Okay. When we did it by calculus here, we actually got the exact number. We got the exact value using calculus. Okay. Let's go ahead and do one more example. Thankfully, this section does not have quick checks. You guys would hate me if it did. I want you guys to take some time with this, really. Excuse me. So let's go ahead and do this next example. Two cars leave a steakhouse at the exact same time. A car A travels north at a speed of 60 miles an hour. Okay. And a car B travels east at 40 miles an hour. How quickly is the distance between them changing 1 hour after leaving the steakhouse? Okay. So I'm going to go ahead. I'm going to do step one here. Step one is going to be just draw a picture. Believe me, it might sound a little corny, but it'll help. Okay. So here's my picture. Okay, I'm just going to draw an X and Y. Okay. Here's the steakhouse. Steak sounds good, by the way, right now. Okay. And this guy, here's the car that's traveling north. This is car A, right? And he's moving that way at, I'm going to write it over here. So he's going 60 miles per hour north. And here's car B. He's moving that way at 40 miles per hour. He's going east. Okay. We need to find how quickly is the distance changing between them 1 hour. So I'm going to go ahead and do this. I'm going to do at 1 hour. So the picture that I'm drawing right here is specifically at exactly 1 hour after they both leave the steakhouse. Okay. That means that this distance after 1 hour is 60 miles. Actually, let me go ahead and use another pen here. This distance right here is 60 miles. And this distance right here is 40 miles. And we want to find how quickly the distance between them is changing. We want to find this. So I'm going to go ahead and define a length here. This is going to be a capital D. Okay. That is the distance between them. Okay. Okay. Let's go ahead and do the rest of step one. Number one. I know I have one here. I'm going to do, this is going to be sort of like the mathy portion of it. Okay. So number one is now we're going to identify all of the variables, all the expressions that we need. Okay. And what I'm going to do is I'm going to go ahead and give a couple more variables here. I'm going to call this one the X. I'm going to call this the Y. Okay. So looking at our picture, what we have here is we have X after 1 hour, right, is going to be 40 miles. Okay. Y is going to be the 60 miles. Okay. Here comes the fun part. We have to now denote some of the calculus that we need to write down. Okay. We have dx over dt. So we have a rate of change in how fast car A is moving. This is the 60 miles per hour. Okay. And we have dy dt. That is the rate of change for car B. Did I mix them up already? Yes, I did. I mixed them up, my bad. So this is going to be 40. Yeah, this one's going to be 40. And this one's going to be 60 miles per hour. My bad. Okay. The last thing is, what is it that we're looking for? We're looking for how quickly the distance between the two cars is changing. We are looking for the big D over dt. This is the I have no clue. Okay. We are looking for the change in big D, the change in the distance with respect to time. Okay. We're looking for the rates of change in the distance, big D, with respect to time. All right. Number two. Part two, remember how I explained it, is one of the harder parts. We need to find an equation that relates all of the values that we're possibly going to get. Okay. Now, if you guys sort of take a second to look at our picture, right? That looks like a triangle. It's got an X and a Y, and it has a hypotenuse D. Okay. So we can, it doesn't matter which one you want to sort of think about. You can either think about the distance equation or Pythagorean theorem, both of which are valid. What I'm going to do is I'm going to use the distance equation. So the distance, that big D that we have there, right, is going to be equal to the square root, right, of the x squared plus the y squared. Okay. This relates all of our stuff. So D is the square root of x squared plus y squared, which is equivalent to, I'm going to go ahead and change it so we can do some calculus on it, x squared plus y squared to the 1/2. Okay, here comes step 3. Step 3 says do the implicit differentiation of everything with respect to time. Okay, so I know you guys hated implicit differentiation when you guys were doing it as a section. Now we're going to actually do it with respect to a scenario here, right? But the work is still the same. Okay, So I'm going to go ahead and start off, right? I know that d is equal to x squared plus y squared to the 1/2, right? So then therefore, if I take the derivative of both sides, right, this is going to be dd over dt is equal to, I need the derivative of something to the 1/2. That's going to be 1/2 x squared plus y squared with negative 1/2. And now comes the derivative of the inside. So it's going to be 2x dx over dt plus 2y dy over dt. Here is our derivative. Go ahead and highlight it in blue. And notice our result has all the stuff we sort of figured out from part 1. Okay, so now that's step 4. We get to plug in all the good stuff. So dd over dt is equal to 1/2 x squared. So my x is 40 plus y squared 60 squared to the minus 1/2 times 2x 40 dx dt, which is my 40 miles an hour. So this is going to be a 40 there, plus 2 times y, that's my 60 miles, okay, times dy dt, which is 60 miles per hour. Keep in mind of that the two 60s are not the same. Okay, the two 60s are not the same. So then this should be equal to, here we go. Making sure I'm not losing anything. Yeah. This is all on the numerator. This is going to go in the denominator. So I'm going to go 2 times 40 squared. I'm going to go ahead and do this. 2 times 40 squared plus 60 squared all over the square root of 2 times 40 squared plus 60 squared. Okay. If you do this properly, you should get something along the lines of 10/4,000 over 2 times the square root of 5,200. And this is all equal to 72.11 miles per hour. So at 1 hour, per hour. There we go. Here's our final answer there. And to summarize, it's all of this thing right here. Okay, so at exactly 1 hour, when they're 60 miles north and 40 miles west or east, the distance between the two cars is increasing at a rate of 72.11 miles per hour. That's how fast big D is increasing between the two cars. Okay, notice how for both of them, for the example before and this example, we are using, the derivatives and implicit differentiation to get that rate exactly, get the rate exactly. Okay, this is going to take a while. Okay, rewatch the video if you need to. I don't think the online homework is going to be that involved this time. I think it's only a few problems. So look at your answers, make sure you understand all the steps, all the bits, and all the pieces. And I believe that is it for this section. Next comes lecture questions. So this concludes the lecture for section 4.1. If you guys have any questions, I'm going to be in my office hours, or in my lab hours, every Monday through Thursday from 3 p.m. to 6 p.m. You can talk to me through discussions, or you can talk to me through emails. Okay. Besides that, I'll see you guys around. Hopefully you guys come visit.